Hi, welcome students. This is Dr. SIVA from the Department of Physics and Nanotechnology, SRM Institute of Science and Technology, Chennai. In this subject, Advanced Computational Techniques, today we will discuss about the silicon nanoelectronics. In this session, we will discuss silicon nanoelectronics and how silicon devices behave when scaled down to nanometer dimensions. We focus on MOSFET operations. We focus on MOSFET operations, how it behave when we go downscale. Then mobility integrations, charge carriers, how they behave once they move. That is called mobility behaviors. Okay, so we'll discuss those things and also short channel effects along with the key nanoscale device limitations. Let's see one by one. Before that, we will understand about the how silicon is actually being originated, how we are actually extracting the silicon like that way. Silicon, which is actually which was identified by Johns Joseph Berzelius in 1823. The name comes from Latin word silex. Silicon can be extracted from silica sand using carbon or aluminium through chemical reduction reactions. Silicon became dominant because it forms a stable oxide material. Silicon become dominant because it forms a stable oxide, which is essential for transistor fabrication. In nanoelectronics, silicon continues to be used due to mature processing, CMOS capability, predictable electronic properties. In nanoelectronics, silicon continues to be used, none other element like the way we use silicon, because it is due to the mature processing, CMOS capability, and predictable electronic properties. And also, most importantly, the native oxides being generated by the silicon, which is silicon dioxide. Let me see here. We have let me have a silicon uh, wafer in this substrate. Okay, when we heat treat it, okay, surface will become, so this all the area will become SiO2 layer. Okay, SiO2 layer, which is a dielectric material. Okay, very important dielectric material in and also it is actually a insoluble insoluble in water. Okay. So this element which forms silicon dioxide is very good, which reduces so much amount of cost price in making a insulation layer with some other element with some other uh, insulation layer. So in several advantages, we are actually going for silicon. It is not only based on the abundant in the earth. We are actually going for several reasons. Let's see here how silicon is actually being fabricated in terms of wafer. You can see the raw material, which is actually polysilicon nuggets purified from the sand, which will be actually taken, and crystal pulling will be actually happening, and silicon crystal ingot formation. Then it will get sliced like thickness like less than a centimeter thickness, like point one or 2 millimeter thickness. Okay, like sorry, centimeter thickness. Okay, 2 millimeter, 1 millimeter thickness of silicon slices will be actually obtained. Then final wafer will be actually polished one side and it get cleaned. Inspection will be actually happening. Then the silicon will be actually fabricated with microelectronic circuits. A MOSFET is a metal oxide semiconductor, okay, which will be actually obtained with the silicon. Okay, so let's see that. Okay, MOSFET. MOSFET is a metal oxide semiconductor device. Okay, MOSFET is a stands for metal oxide semiconductor field effect transistor, or metal oxide semiconductor field effect transistor, also called as insulated gate FET. Okay, this is also called as insulated gate FET. Okay, for over 40 years, MOS devices have been scaled to increase density, reduce power. Every technology generation reduced delay by about 30% and doubled performance every 2 years. Again, I'm repeating. For over 40 years, metal oxide semiconductor devices have been scaled to increase density. Density was actually keep on increasing, and power is actually keep on decreasing. Consumption of power is actually keep on decreasing. Every technology generation reduced whenever the new technology comes. Okay, one to another. Okay, there will be a delay will be there, which will get reduced by 30% and doubled performance every 2 years. Okay. Every 2 years, the performance will get doubled, which is the Moore's law. The supply voltage VDD has been scaled down to manage the required power inside the device completely. Let's see what is a short channel device. Okay, so this is what the MOS device. You can actually see here a transistor. So here in this you can actually see the p-type substrate being taken here, in which this region is actually being doped with n plus atoms. Dopant atoms are actually being doped here, like it will become n type here. Okay, n type silicon, and this region will also be n type silicon. Okay, in order to represent for a simple. Okay, let's consider a wafer surface in this one particular place. Okay, and another particular place being doping. Doping process. Okay, doping process. So once we dope, this region and this region will be actually converted into n type if it is p type. Okay, we'll be taking n type doping here, and we can easily understand it is actually the n type region. Okay, n type region, and the second one is p type region, and here the n type region. So it is an NPN transistor. Once we heat treat this surface will become oxide layer, which we call it as silicon dioxide. And due to this silicon dioxide formation, which is actually a dielectric layer, because of this reason, we called this device again by means of the insulated gate FET. Okay, we called this in terms of insulated gate FET. Okay, so gate is actually got insulated. Okay, now this region in this diagram you can see this region. Let me consider region 1. Okay, and let me consider region 2. See, they are depletion region, which we can see easily understand. Okay, since the power supply is actually flowing from one to another end, accumulation of charge carriers will be there. So due to that reason, this drain region and this source depletion region get differs in terms of thickness. Okay, Hope you can understand. Now the problem what we are actually going to discuss is this distance when it is actually being reduced. Okay, we do not bother about this one. We do not bother about this region. Only the gate thickness when it is actually being downscale. Okay. So what are all the problems are actually being raised there, which we are actually going to discuss now in this class. What is a short channel device? Let me clear everything. Okay. Again, the same device you can actually see here. What is a short channel device? A MOSFET becomes a short channel device when the channel length approaches the depletion width near the source and drain. When the channel, or you can see the gate length, which is actually approaching the very equivalent to the thickness of source and drain, as small as that we can actually take. At this scale, electric fields from drain and gate, electric field from drain, electric field from drain region and gate region, okay, which overlaps each other, altering the current control. Traditional long channel models no longer accurately describe this behavior. Traditional long channel models, which is actually the micron sized or the devices, whatever we have actually used so far, okay. So they are actually no more, they are actually not no longer accurately described this behavior. But once come down to the nanoscale, these are all the major problems. We can measure the short channel length also, okay. We can actually measure the length, okay, and current also. This is called a short channel current. Okay. See, short channel effect. As drain voltage increases, as the drain voltage increases, the drain depletion region widens. Okay, so this region will get wider. This shift the pinch off point toward the source. Since the drain depletion region keep on widening, effectively shortening the channel occurs. We can easily understand that once it is actually small in size, this size depletion region of the drain will become dominant than the gate length. Again, I'm repeating here, the drain depletion region widens, effectively shortening the channel in another way. This shift the pinch off point towards the source. This behavior is modeled by modifying the drain current equation, showing the dependence on reduced effective channel length. So as the channel length shrinks, as the channel length being reduced, source and drain depletion regions become comparable to total channel length. The potential distribution becomes two-dimensional and depends on both transverse, which is gate controlled, and longitudinal electric field. Longitudinal electric field in this, which is drain controlled. This causes threshold voltage variation, reduced saturation. This causes threshold voltage variation, reduced saturation. Okay, let's say here again. As the channel length reduces, okay, channel length is actually reduced, the depletion region widens the source and drain junction becomes comparable to the channel length. The potential distribution becomes two-dimensional. The potential distribution becomes two-dimensional, okay, and it depends on both transverse and longitudinal electric field. Transverse electric field and longitudinal electric field. So, which are actually controlling this. This causes the threshold voltage variation. This causes the threshold voltage variations, reduced saturation, and punch through effects. Mobility degradation. Mobility is an important factor, okay, in the device, because which are actually the how faster we can say the device. Current in a MOSFET depends on carrier mobility. In short channels, mobility get reduced due to two mechanisms, which is actually getting degradation by means of two mechanisms. One is lateral field effect and another is vertical field effect. Strong lateral fields cause velocity saturation. Strong lateral field causes the velocity saturation. Okay. So velocity saturation occurs. The lateral field is increased at that time. The channel mobility becomes field dependent and eventually velocity saturation occurs. This is resulting in current saturation. So mobility have got reduced. The next one is vertical field effect. High vertical fields increase surface scattering of carriers. High vertical field increases the surface scattering. Both lower the mobility and reduce the current capability. See, short channel effects. What are all the short channel effects? In nanoscale MOSFETs, 5 physical effects must be considered. One is very important one, drain induced barrier lowering and punch through. Surface scattering, velocity saturation, impact ionization, hot electrons. These effects define modern scaling limits. Once we do any device at a nanoscale or beyond the nanoscale, these are all the major things which are actually affecting the device. So we need to actually be very cautious while we design the new circuits. Drain induced barrier lowering. In short channel, the drain voltage lowers the potential barrier between source and the drain. In short channel, okay, let's consider here. So this is actually the short channel, okay. In short channel, the drain voltage, okay, get lowers, okay. So now it is actually getting lowers here, okay. Notice, okay, it is getting lowers, okay, like this way. This earlier value due to short channel, it get lowers. The drain voltage lowers the potential barrier. This is the potential barrier which get lowers because of the drain voltage level, okay, and this causes effects. Electrons can flow, electrons can flow even when gate voltage is below the threshold voltage. So easily they can actually flow. Earlier it cannot actually flow, so it will find difficulty here, and it will not go like this way. If the gate voltage is below the threshold voltage, so it cannot occur, but in this it occurs. This subthreshold conduction increases. Subthreshold conduction value get increases the leakage current and reduces the threshold voltage control. This gate will be actually having the threshold voltage control, which is got degraded, and all these things are actually being arised due to the drain current. So due to this reason, it is called to be drain induced barrier lowering. Drain induced barrier lowering. It is being induced by drain. Barrier got lowered so that even in the subthreshold voltage, the current get flows like this way here. Okay, not in this. Okay, due to the energy band diagram. In short channels, the drain voltage lowers the potential barrier between source and the drain. Electrons can flow even when gate voltage is below threshold. This threshold conduction increases leakage and reduces threshold voltage control. Punch through. When the drain depletion region extends to, when the drain depletion region extends to source region, we discussed in the previous, a continuous depletion path forms. This allows current to flow without any gate control. The gate will not be actually having any control. Source to the drain. Okay, source to the drain. Without any control, it actually flow. This allows current to flow without a gate control, increasing the leakage current and reducing the threshold voltage. Punch through is minimized with a higher substrate doping, thinner oxide and longer channels we can actually obtain. So this can actually obtain with a thinner oxide layer or longer channels or higher level of substrate doping. So this can be actually controlled, which is called, which we discussed, called punch through. Surface scattering effect. Okay. In nanoscale geometry, in this geometry nanoscale, carriers are pushed towards the oxide interface by vertical electric fields, by means of vertical electric fields. Okay. So the collisions at the interface reduce the mobility. At the interfaces, the collisions of the charge carriers will be there, which can actually reduce the mobility. Surface mobility becomes much lower. Surface mobility will become much lower than the bulk mobility. Make a conduction more resistive. This conduction will be actually good initially, but it will get reduced. So resistive will become raised. That is called surface scattering. Collision of the electrons causes a reduction in the mobility. Electrons moves with great difficulty parallel to the interface. The average surface mobility is about half as much as that of the bulk mobility. So drastically reduced into half value. So surface scattering is actually an important one. The next one is called velocity saturation. Okay. At low fields, carrier velocity increases linearly. At low voltage level, the carrier velocity increases linearly with the field. At high fields, velocity saturates at approximately 10 to the power 7 centimeter per conductivity. This reduces transconductance and limits current value. This reduces transconductance and limits the current value, especially in short channel devices, which is called velocity saturation. Velocity saturation reduces the transconductance of the short channel devices in the saturation condition conduction, as the following formula, where Gm is equal to W into C into B. Impact ionization. The presence of high longitudinal fields can accelerate electrons that may be able of ionizing silicon atoms by impacting against them. Okay, let's discuss here. High electric fields can accelerate electrons through uh, which are actually enough to knock atoms and generate electron hole pairs. High electric field can accelerate electrons enough to knock the atoms and generate electron hole pairs. Holes accumulate near the source. Okay, source and gate and drain. Holes get accumulated. Okay, holes get accumulated near the source, which causes the forward bias of the source substrate junction. Source and substrate junction. In this, it causes the forward bias. Okay, we studied uh, plus minus with forward bias condition. So we know very well what it is. So which that kind of conditions will be actually obtained automatically. So H plus will be actually keep on accumulated very close to the source region, which can actually create the forward bias. This leads to reliability issues and local heating effect. So this region can actually create a reliability issues and heat. Okay. Also, this injecting the new electrons. This is a problematic. Next one is called hot electrons, which is last one. In high voltage of drain source voltage conditions, okay, at a large VDS, okay, energetic electrons can overcome the silicon dioxide layer, which is the interface barrier, and become trapped in the oxide layer. The electrons go into the oxide layer, SiO2 layer, okay, silicon layer. This leads to permanent device degradation, threshold voltage, which will get shifted, and reduced lifetime of the device we found. So with this, we can actually wind up the topic on downscaling effects of silicon electronics. So due to these kind of defects only, we are actually moving for the new technology or new materials which can actually overcome, or which will not actually find these kind of problems, like carbon nanotubes, MOS2, and other new materials. Thank you, students. We will be actually discussing all those topics in the coming sessions. Thank you.